All right, so this is a quick makeup video that we're going to go through to make up for, I believe it was lecture 9. This was the lecture where we went through and did a full-blown design example of a tension member. We had some technical issues during lecture, so I decided to post this quick video just summarizing the results of the example. So just a little bit of background, we were going through tension member design, and if you recall, we had derived the following expressions for design, solving for a required gross area and a required radius of gyration. Big thing to keep in mind is that this was based on an assumed effective net area, and that where we incorporated this additional 0.75 in the denominator. So when we select a member, we're going to have to go through and subsequently analyze it in order to assess its capacity. Now we can validate or assess a design by calculating its efficiency, just the load over the resistance. And a good rule of thumb is if that value is larger than 90%, if 90% or larger, then the member's most likely a pretty good design and probably the most economical one. Okay, so here's the example, and again, I'm going to go through this somewhat quickly because we did cover this in class, but also that's sort of the beauty of YouTube. You can always pause this and make sure you're getting all the details. But we're selecting a W12 section, so it's a W12 by something. It could be a W12 by 48, W12 by 55, what have you. And ultimately, we're just trying to select the most economical section. The member's 30 foot long, it's subjected to a dead load of 130 kips, a live load of 110. The reduction's already happened, so you don't need to worry about all of that. Here's the parameters for the connection. We got 4 bolts through the cross section, 2 lines of bolts in each flange, 3 bolts per line, 4 inches spaced out in between. And for our assumptions, we're going to use 7/8 inch diameter bolts, and we're going to assume a 992 steel. So let me go ahead and drag over this PDF. Now, a couple things about this. The PDF says example 4, but this actually is, in fact, example 5. This is off of the notes from last year. And last year, the difference is I added an additional example in the beginning, so that's why it's an example off. Also, I am sorry about the sort of the sketchy or the gritty words that pop up every now and then. The conversion software that converts this smartboard annotations to PDF can be a little sketchy at times, so I apologize for that. Okay, so let's just sort of really quickly go through the examples. So we started off with a dead load of 130 kips and a live load of 110 kips, and that indicates that we need to factor them. So we really need to go through and assess all of the possible load combinations. But really, when all you have is just a dead load and a live load, you really only need to assess 2 of them. 1.4 times the dead, and then 1.2 dead plus 1.6 live. And this one's more often than not going to be the one that governs. And as you can see, that's what happens here. Go through and chug it out, and you'll get 182 kips for the first load combo and 332 kips for the second one. So as you can see, 332 kips obviously is the one that governs. Now we take that and we say, all right, we've got a 992 steel, so we go to table 2-4 in the manual, and then that'll yield a yield stress of 50 KSI and a tensile stress of 65 KSI. That's unique for A992. And then using those, we can calculate some design expressions. So we calculate our minimum gross area, so it's the factored load, PU, so that's 332. Divided by the minimum of 2 quantities, either 0.9 times the yield stress or 0.75 squared times the tensile stress. So go through and chug all of that out, and you'll find that the minimum quantity is the one over here on the right, and that comes out to be about 36.56. So chug it out and you get a gross area requirement of 9.08 square inches. So that indicates that we must select a member that has at least a gross area of 9.08 square inches. We can calculate a similar one, a design expression for a radius of gyration. So R min is L over 300. Now the member's 30 foot long, but the big thing is it's 30 foot long, you have to convert that. So we have to adjust that and turn it into 360 inches, so 12 inches per foot. We have to include that. So plug and chug, and we get a radius of gyration of 1.2 inches. So that means that when we select a member, we have two requirements that we're selecting based off of. We need a gross area of 9.08 square inches, and we need a minimum radius of gyration of 1.2 inches. So you go through the manual, go through all the W sections, and trying to find the lightest section that you can. Keep in mind, lightest, we're going off of that number right there, the 35. Because remember, the 35 indicates 35 pounds per foot. So go through the manual and try and find the lightest one that you can, and you will in fact find that a W12 by 35 meets these two requirements, an area of 9.08 square inches and a minimum radius of gyration of 1.2 inches. And here's all the associated properties. So you can see the gross area is 10.3 square inches, and the minimum radius of gyration for a W section that's RY is 1.54. So keep in mind, however, that, okay, we've got a section that we can start working with, but this is a trial section. It's a trial section because we have to validate the assumptions that we made earlier. Because essentially, when we use, going back a slide, when we use this design expression here, we are assuming a shear lag factor and assuming a thickness in a roundabout way. So we have to verify those assumptions, and that's basically by checking the capacity. So verifying the capacity of the W12 by 35, I guess the key number to keep in your head is this one, that the factored load is 332 kips. So first thing I'll do is I'll calculate gross section yielding. Gross section yielding comes out to be 0.9 FYAG, which factor all that out and multiply that out, comes out to be 463.5 kips. So if I compare this number right here to the factored load of 332, we can see that I'm okay because the yielding capacity is larger than the load. Or an easier way of understanding that is this number right here is how much the member can withstand. This number over here, that's how much I'm actually loading it with. I'm pulling on it with 332 kips, and it can hold up 463. So this is a good result. But this is just gross section yielding. We have to go through and do net section fracture. So we have to calculate net area. Remember, this is a W section with holes in the flanges, and you can see 1, 2, 3, 4. So if I cut a section through that wide flange, I'm going to be cutting through 4 holes. So I need to, for my net area, I need to subtract 4 bolt holes. So the gross area minus 4 times the diameter of a hole, which is the bolt diameter plus 1/8 of an inch, times the flange thickness, which comes out to be 0.52 inches. So plug and chug, and you get about 8.22 square inches. Pretty straightforward. For shear lag factors, we have 2 cases to assess. So case 2, we have the connection length, which is 8 inches, and you can see that right here, just 4 and 4, there's your 8 inches. For X bar, remember our X bar for a W section that is connected via the flanges is the Y bar of the equivalent WT. So since we're dealing with a W12 by 35, just cut each of those numbers in half. So 6 for the depth and 17.5 for the weight. Look that Y bar up and you should get 1.3 inches, and that's in table 1-8 of the manual. So the U for case 2 is 1 minus X bar over L, so plug and chug and you'll get 0.838. Now that's not the only case that we assess. We also can employ case 7. So the flange width is 6.56 inches, 2/3 of the depth. Remember, we're always using decimal values, no fractional values for our quantities in the manual. So the depth is 12.5. Plug and chug and you get 8.33. Since the flange width is less than that, that means that U7 is a 0.85. And remember, when you've got this quantity and this one right here, if you calculate per case 2, the larger value is to be used. That means we use the U7, 0.85. So we can calculate net section fracture. So phi PN is 0.75 times our tensile stress times net area times the shear lag factor. So 0.75 times our tensile stress is 65 KSI. Net area we did on the previous panel, that was right here, 8.22 square inches. And then the shear lag factor we just did is 0.85. Chug all that out and you get a capacity of 340.6. And this is very good because think here, this number here, that is our capacity. That's how much the member can withstand, and we're putting 332 kips on it. This is a great result. This is a very efficient design. If you take the load and divide it by the resistance, you get an efficiency of around 97%. So that's an incredibly economical design. We definitely wouldn't want to go lighter than the W12 by 35. So the answer for this problem, the actual design, is use a W12 by 35. Okay, that concludes it for this video. We'll see you next time.